Everyone was like way too excited about it.
Everybody have a good weekend?
No. Too short.
Too short? Same length as any other weekend,
I know.
except for the one coming up. Always too short? So last time we started talking about functional groups. How could we identify functional groups? Pardon? Okay, find heteroatoms. And what's a heteroatom? Anything that's not a carbon or a hydrogen, right? So if we can find heteroatoms, typically we're going to find the functional groups. Okay? What else can be found in functional groups? Pi bonds. That's right. So if we find double bonds and triple bonds or heteroatoms, we're usually in a pretty good place to find the various functional groups. Okay? So we're going to continue to talk about functional groups today, and we're going to review a little bit of what we talked about yesterday. I sent a pencast to you all yesterday on some of the functional groups that we weren't quite able to get to. What were some of those functional groups that we weren't able to get to on Friday? Okay, so things that contain the carbonyl group, and carboxyl, like the carboxylic acid, was certainly one of them. What are some other functional groups that contain the carbonyl, the C double bond O? Pardon? Amides. Okay, what else? Aldehydes. Ketones. So we got carboxylic acids, we got aldehydes, we got ketones, we got amides. Ester. Yep, that's another one. And acid chlorides or acid halides were another one that were in that list. Okay? And it turns out that the carbonyl group is very, very common in functional groups that are very, very important for organic chemistry. Okay, we're going to talk a little bit about physical properties as well. And functional groups tell us something about physical properties. Certain functional groups can hydrogen bond, for example, others cannot. And so that helps determine what types of physical properties and attractive forces that we'll be dealing with. Okay? So let's look at some examples of some of the carbonyl-containing functional groups like carboxylic acids. Okay? Formic acid is the simplest of the carboxylic acids. What do you all know about formic acid?
Ant bites.
Ant bites. This is exactly what fire ants will inject into you when you step into an ant bed, and it hurts, right? Formic, pardon?
Well, he said, is that why I'm allergic to them?
It's probably not the formic acid is the reason why you're allergic to them. You'd be allergic. It's much too small a molecule to elicit an allergy. It's not just pure formic acid that they inject you with. Okay. In fact, just for your information, in the old days, the really old days, one way that chemists would actually get formic acid to utilize was they would distill ants. They would go out and they would find a big mound of ants and they would collect the mound and you would actually distill. You'd heat them up and they would pop open and the formic acid would distill out and you could collect it. Imagine trying to do that. That seems very, very difficult to me. Okay? But it is the simplest of the carboxylic acids. And what do we recognize when we look at this functional group? Right? We see a carbonyl, right? And what looks like an alcohol. Do not think of it that way. It's the carbonyl group and the OH all together that is the carboxylic acid functional group. The carbonyl is also connected to a hydrogen, and that's what makes it formic acid, because it is the acid derived from formaldehyde. Okay? Propanoic acid, another simple carboxylic acid. How does this differ from formic acid? Yeah, there's an alkyl group, in this case an ethyl group, absolutely, that's attached to the carbonyl, right? So replacing the hydrogen on the carbonyl with the carbon group is the difference that we see here. Okay? But other than that, the functional group's identical, right? It's still the carboxylic acid functional group. Okay? Benzoic acid. Notice we've replaced the alkyl group with what kind of functional group is that ring? That's a phenyl ring, or it's a benzene ring. That's right, it's aromatic. This is an aromatic containing carboxylic acid. But the function, it has still the carboxylic acid functional group. You all know of benzoic acid as its sodium salt, sodium benzoate. Can anybody tell me where you may come into contact with sodium benzoate? How many of you like to go eat Chinese buffet? Huh? Soy sauce is preserved, typically. The Kikkoman soy sauce is typically preserved with sodium benzoate. It's a nice food preservative, okay? And it's the salt of that benzoic acid. Okay? Esters are somewhat like carboxylic acids, except what? Okay, we don't have any OH, right? We have an OR of some type, some carbon group out there, right? Can anybody tell me what you know about esters?
They make stuff smell.
Okay, they do have a typical aroma with them. They are not aromatic, but they do have a typical aroma. What kind of smell? Pleasant? Unpleasant? Typically, esters are pleasant smelling, whereas carboxylic acids are kind of smell like vinegar. I mean, they just don't have a terribly pleasant odor with them. However, if you put on cologne or perfume this morning, you were putting on a mixture of esters. Okay? Flowers make these nice smelling esters that are useful for perfumery and other types of things like that. Okay? Amides. Okay? We can have 3 different flavors of amides, if you will. How do you distinguish those? How would you label those? Primary, secondary, and tertiary. And what determines that this is a primary amide? There's one carbon-nitrogen bond. Okay? This is a secondary amide because there is the carbon-nitrogen bond to the carbonyl, but there's also the carbon-nitrogen bond between R prime and N. Okay? And then a tertiary amide has 3 carbon-nitrogen bonds. Very important in biology is which one? Primary, secondary, or tertiary? Not the tertiary. Not the primary. That leaves the secondary. That's right. Process of elimination here. It is the secondary. The secondary amide is the protein or peptide backbone of all your proteins and peptides. This is how amino acids come together and form these biopolymers that we call proteins. And it's through this amide bond that is so important. Okay, now organic chemists call these amides and amide bonds, but in your biology classes they will frequently refer to these as peptide bonds. It's the same thing, different term. Okay, so kind of important stuff. Nitriles. What's a nitrile? Okay, carbon-nitrogen triple bond. What is C triple bond N that you remember from general chemistry? Not cyanate, but cyanide, right? You all talked about things like sodium cyanide and potassium cyanide. These are organocyanides, if you will, okay? They are not cyanide because there's not a negative charge on them, okay? And they're not salts. But they are not as toxic. Organonitriles are not toxic like sodium and potassium cyanide are. Okay? What do you all know about nitriles? What are they useful for? Gloves. That's right. You've probably worn nitrile gloves before in the lab. Why would we want to give you nitrile gloves as opposed to latex gloves? There are a significant number of people who have a latex allergy. That's exactly right. Have you ever seen anybody have an attack from a latex allergy? It's not pleasant. It could be quite serious, actually. And so nitrile gloves, no latex allergy. Okay? Rarely will you go into an office, like a doctor's office or a laboratory now, and find latex gloves. They've been, I wouldn't say banned or banished, but you can get nitrile gloves just as inexpensive, and you don't have to worry about the allergy issues. Okay. Some examples of nitriles. This is known as ethane nitrile. That's not how chemists typically refer to it, though. We typically refer to it as acetonitrile, and it's a very, very good organic solvent. Very useful in a variety of reactions and analytical techniques that we use. Acetonitrile used to be extremely cheap. You would buy it by the 50-gallon barrel, and it was basically, you pay a little bit for it, and you pay most of the cost to get it shipped to you. It was a byproduct of certain polymer-making processes. However, these days, acetonitrile has gotten much, much more expensive because many of those plants in the United States that made that particular polymer process have shut down. And so supply and demand is always there. Okay. Butane nitrile. Benzene carbonitrile is another example. So any carbon group can be attached to the cyanide, basically, and it will be a nitrile functional group, okay? And so here's another example where we don't have an aromatic ring. We just have a 6-membered carbon ring. But in all cases, those are nitriles, okay? So we learned about some of these last time, right? What's the functional group for an alkane? Remember, we really don't consider it a functional group, right? I mean, it's just a pure hydrocarbon without any pi bonds or heteroatoms. Does it have a function? Yes, its function is to burn. That's basically all we can do with alkanes, okay, in terms of chemistry. What about when we go to alkenes, what's the functional group? The double bond, that's right. And when we go to the alkyne? The triple bond. And the aromatic ring, it's the aromatic ring, right? And if this is a chlorine, this would be an alkyl chloride. If it's an iodine, it would be an iodide. Alcohol, ether, right? And so here's some examples down here of all these things. And we'll learn more about the naming of these as in the next chapter. But what you should learn is that there's a difference between IUPAC and common, right? And do you need to know both of them in this class? Absolutely. You will need to learn common names as well as IUPAC names because that's the way we work in the world, okay? We quite frequently do not call things by their IUPAC name, okay? There's a lot of history behind a lot of things. But for example, this is ethene by IUPAC name, but we typically call it ethylene. Right? And when you go buy something that's been made into a polymer from this, you don't call it polyethylene, you call it polyethylene. And that's how all the polymer people refer to it. It's not polyethylene, it's polyethylene, even though both names will be absolutely correct. Here's some of the other ones. Here's an amine, right? Carbon nitrogen, notice it has to be bound though to what? What kind of carbon? Just a regular carbon. It can't be bound to a carbonyl. If it's bound to a carbonyl, it becomes an amide. That's right. And so if we have one carbon-nitrogen bond, it's what kind of amine? Primary. And 2? 3? Okay. All amines have to have the lone pair of electrons on the nitrogen. But technically, we can add a 4th bond to that nitrogen. Would it then be an amine? No. Then the nitrogen becomes positively charged and it actually becomes what's known as a quaternary ammonium salt. And they are not amines. They do not have the chemistry of the amine. This little molecule right here is methylamine, CH3NH2. Can anybody tell me what popular show made big deal of methylamine? Breaking Bad. That's exactly right. What were they using methylamine for? Methamphetamine. That's exactly right. Methylamine is a controlled substance because of that. Anybody with just basically the chemistry that you're going to learn this semester will have enough chemistry under their belt to take the materials and go make methamphetamine. It's the easiest molecule in the world to make. So what do we do to try to control it? We control the availability of the materials. That's why Walter White had to go and hijack a bunch from a train, in that one episode to get the methylamine that he needed. Because you can't just go down to the grocery store and buy a good old bottle of methylamine. Just can't do it, okay? They control those things. The aldehydes, ethanol is an example. We know it more commonly as acetaldehyde. Can anybody tell me where this comes from? This is the aldehyde that gets produced in your liver when you drink too much alcohol. Well, actually, when you drink any alcohol. Okay? Your liver processes the alcohol into acetaldehyde, and it's the compound that is responsible for hangovers. It is the compound that is responsible for you getting dehydrated if you drink too much, which is not a good idea. Okay? And that acetaldehyde is ultimately oxidized further in your liver to acetic acid. Pardon? Somebody have a question? All right, so I cannot overstate the importance of functional groups. Can't be overstated. You have to know these. There's just no ifs, ands, or buts about it. It's not something that you can learn just before the exam. You have to know them forwards and backwards, because functional groups are going to give us the shape of the molecule that we're talking about. It's going to help determine the intermolecular forces, which are important for the physical properties. How we name molecules is based on the primary functional group within that molecule. And chemical reactivity is going to be based on the functional group. If you know how alcohols react, it doesn't matter whether that alcohol is in a large molecule or a small molecule. It's probably going to react very similarly. Not necessarily identically, but very similarly. So instead of trying to remember chemistry for the, whatever it is, 9 million organic compounds that are known, whatever the number is, you only have to memorize the reactivity of a handful of functional groups. Okay? So, very, very important. How are you studying to try to memorize your functional groups? Well, it's going to be different for everybody, but one of the things that I recommend is you make your own flashcards. And you carry them with you. And when you have a moment and you're stuck in traffic, you pull out your flashcards. When a commercial comes on TV, you pull out your flashcards. And it's a great idea to put the structure on one side, the name on the other, and shuffle them around and be able to memorize them, okay? You need to be able to see and understand functional groups by sight, okay? So let's do a quick little concept test in here. Let's see, in penicillin G, what is penicillin G? What's penicillin? It's an antibiotic. Penicillin G is just an antibiotic, okay? It's just a member of the penicillin family. How many functional groups do you see in there? Huh? Yeah. How many different functional groups do you see in there? In fact, they're all different. All the functional groups in there are different. Let's focus on them. What do we got? Well, let's start on the left side. What do we got over here? We got an aromatic ring. That's right. What do we have here? We have an amide, but what kind of amide? It's a secondary amide. What do we have here? It's a tertiary amide. Okay, and this happens to be cyclic, which gives it the chemistry that we need for penicillin. We'll learn more about that later. What do we have here? Sulfide. That's right. So it looks like an ether, right, but with sulfur. It's a sulfide. And what do we have here? Carboxylic acid. That's exactly right. Okay? You replace any one of these functional groups and it will no longer behave like penicillin G. There is one functional group in there that's known as the pharmacophore. Can anybody tell me what the pharmacophore means?
It's used in a lot of medicine.
Pardon?
It's used in a lot of medicine.
Okay. Not far off the mark. It is the functional group that is responsible for the pharmacology of the molecule. Okay, you can't change it at all or you don't have the pharmacology. Does anybody know which one it is?
Is it the
This one right here? Yep, that is it. All penicillin molecules have this so-called beta-lactam, okay? And don't worry about that name yet, but they are part of the beta-lactam antibiotics, okay? Without this ring, this molecule is absolutely useless as an antibiotic, and it has to do with that functional group, okay? This is how it kills the bacteria, is through this functional group. Ibuprofen, what you might take after an exam, right? What are the functional groups? I've got a carboxylic acid, and I've got a benzene ring, right? Notice the same functional groups are up here in penicillin G. Carboxylic acid and a benzene ring. So why will we not take penicillin G to cure our headache? Doesn't work like that. Why doesn't it work like that? It does have different functional groups. Okay? So this one not only has the carboxylic acid and the aromatic ring, but it also has the amides and the sulfide, right? And putting those together in those different arrangements gives different function. What I want you to notice is that multiple molecules can actually contain the same functional group, but have very different biological activities. Okay? And that's very, very important when you all are studying to be doctors and other things like that. You need to know that you can have the same types of functional groups in very different molecules, and they will behave differently from a biological standpoint when we start to mix multiple functional groups together. Okay? So, let's talk a little bit about intermolecular forces. Give me some examples of the intermolecular forces that you recall from general chemistry.
London dispersion forces.
London dispersion. What's another name for that? Van der Waals. Both names are perfectly acceptable here. Okay, we have dipole-dipole. We have Van der Waals. Pardon? Dipole-induced dipole. Hydrogen bonding. Ionic. Ion-ion.
Dipole.
Ion-dipole. Yeah. So, lots of examples, right, of intermolecular forces. Is ion-ion going to be really relevant in organic chemistry? No, but every now and then we'll have to rely on it. But it's not as common as what you all talked about in general chemistry. Okay? So, when we have a situation like this is an electrostatic interaction between oppositely charged atoms. In this case, this is a model of sodium chloride, right? And these are just simply ionic compounds. What do we know about the physical properties of ionic compounds? Do they have high boiling points, low boiling points? Very, very high, yeah. Melting points, high or low? Lower than the boiling point for sure. But compared to most things, high or low? Pretty high, right? If I take butter, for example, and I throw it in my frying pan and turn the oven on, what does it do? It melts. Pretty low temperature, right? If I take salt and I throw in my frying pan, what happens? Nothing. I mean, it just sits there. Maybe it dries out a little bit, releases some water, but do I melt it? No. Do I have to worry about it evaporating out of the pan? No, right? They have high boiling points and melting points. Has anybody ever seen molten salt? I've actually melted salt once in my life, and it's kind of a scary process. You have to have a very high temperature to do it, and then you're holding this tube with a pair of tongs, obviously, of molten salt. And it's kind of neat when it cools down and crystallizes into this one nice big crystal. If you ever get a chance to see it, you should see it at least once in your life. However, covalent compounds, which is what we're largely going to be dealing with in organic chemistry, right? We're not dealing with ions so much, okay? So we're going to be really looking at Van der Waals forces. We're going to be looking at dipole-dipole interactions, and we're going to be looking at hydrogen bonding. Those are the three main intermolecular forces that we're going to be concerned with, okay? Now, you all know that Van der Waals forces are weak, right? So we can ignore them, correct? No, of course not, right? Give me an example of something that you use regularly, maybe you do, that relies on Van der Waals forces to give it the physical properties. Any of you ever go to a picnic or something and take home leftovers and you put a saran wrap or something over the bowl? How does the saran wrap stick to the bowl? Van der Waals forces. It's the weakest of the forces, and yet you take this saran wrap and you wrap the bowl with it and you can turn it upside down, and does your stuff come out? Why? Why can a weak force have such a pronounced effect? Because I got a lot of them. That's exactly right. So I take something that's weak and I make billions of them, and all of a sudden that adds up to something fairly strong, right? Okay, very good. It's just like, you know, if I could get everybody in the world to deposit a penny into my checking account, I'd tell you all bye-bye, right? I'd retire. It's a small amount. Nobody would really recognize it, but there's, what, 6 billion people on the planet or something like that? That's a lot of pennies, right? Same thing here, a lot of Van der Waals forces. Dipole-dipole interactions, these are moderate. What do we mean by dipole-dipole interaction? You have to have a permanent dipole, right? Van der Waals forces are temporary dipoles, not permanent. So what would we need then to have a dipole-dipole interaction? How do we get a permanent dipole in a molecule?
Uneven distribution of electrons.
Yep, absolutely right. But how does that come about?
One molecule is more electronegative than the other.
Okay, so I put some electronegative atoms in. So maybe if I have some oxygens or halogens, right, within my organic molecule, now I'm going to set up a permanent dipole. And you all learned about hydrogen bonding in general chemistry, right? Why do we separate hydrogen bonding out? All it really is a strong, what? It's a strong dipole-dipole interaction. That's all it is, right? But it's much stronger than a typical dipole-dipole. And so we call it hydrogen bonding. What are the rules for hydrogen bonding?
Hydrogen has to be bound to a little electron.
Okay, so that hydrogen has to be bound to something like oxygen, fluorine, nitrogen. Yep, fluorine was mentioned, right? Can we have carbon-hydrogen bonding?
No.
Now, if you were in Dr. Wallace's class, he may have said yes. And there are cases where you can see that. For the purposes of this course, hydrogen bonding is really limited to nitrogen, oxygen, and fluorine. Okay, so if you have a hydrogen on a fluorine, you can do hydrogen bonding. If you have hydrogen on an oxygen, you can do hydrogen bonding. If you have hydrogen on a nitrogen, you can do hydrogen bonding. So given that information, what functional group should be able to participate in hydrogen bonding very easily? Carboxylic acids. Okay, what else? Alcohols. Amines. Maybe amides, right? Ketones can accept hydrogen bonds, but they can't donate a hydrogen bond because there's no hydrogen on that oxygen. But it can accept them. You're absolutely right. Okay?
What were the rules for accepting?
Just has to be oxygen, nitrogen, or fluorine can accept a hydrogen bond from something else. Yeah. Van der Waals forces, as we mentioned, are the weakest. We can also call them London dispersion forces or London forces. Okay? And this is what occurs in nonpolar compounds. Pure hydrocarbons have Van der Waals forces. In fact, everything has Van der Waals forces, right? But hydrocarbons, it's really all they have. Why is it all they have? If I take a hydrocarbon, why is it that the only intermolecular force that can have is Van der Waals interactions? That's right. So carbon and hydrogen, what's the electronegativity difference? Great or small? Very tiny. So there's really no permanent dipole, so to speak, right? And when we draw this out like this, right, this hydrocarbon, what are we assuming in terms of our Lewis structure? We're assuming tetrahedral geometry. That's true. But we're assuming that the electrons are between two atoms all the time, right? Exactly between them. But every now and then, can't the electrons kind of move around a little bit, even within a bond? Absolutely. And so what happens is, in this case we're just looking at methane, sometimes the electrons will be more to one side than the other, and that creates a temporary dipole. And if I have a temporary dipole in this molecule, what does that induce in the adjacent molecule? Another temporary dipole, right? And so you can have this temporary dipole interaction that allows us to have these intermolecular forces that actually can add up. So pentane is a liquid or a gas at room temperature?
Yes.
It's close. I can actually boil it in my hand, but it's actually a liquid. What about methane? It's a gas. What's the difference? One's bigger than the other. What else? More carbon. What else? More van der Waals. And how do I know there's going to be more van der Waals interactions with this molecule than there is with that molecule? All right, yeah, it all has to do with surface area. Right? If I look at the surface area of this molecule, it's got more surface area to interact with another molecule, whereas methane is pretty small. Very little surface area to interact with another molecule. So what does this tell us? As we get more surface area, van der Waals interactions become more important or less important? More important. And how much surface area do I have with my saran wrap? A lot, right? I pull out a sheet of saran wrap. I don't have just a little tiny amount of surface area. I've got this sheet, right? And have you ever had a piece of good quality saran wrap fall over on itself? And then you try to, and you're sitting there all frustrated, right? It's nothing more than temporary dipoles that are giving you that frustration. But you've got billions and billions of those interactions in that big sheet. And that small amount of force adds up to a frustration, right? As we try to flatten out the sheet so we can put it over our bowl, okay? So van der Waals forces are going to be very, very important in organic chemistry, especially for things that are nonpolar, okay? So if we look at some examples here where we have pentane and neopentane, how are they related to one another? What kind of isomer? Structural or constitutional isomer. So they have the same molecular formula, don't they? Pentane has a boiling point of about 35 degrees. Human body temperature is 37. That's why I can boil pentane in my hand. Okay? Neopentane, do you think is going to be higher or lower than that?
Higher. Weaker because of the smaller surface area.
All right. They have a smaller surface area, so are we going to have more molecules interacting or fewer molecules? Fewer, right? And so if I have fewer, that's going to be weaker overall, and that means my boiling point is going to go up or down? Down. That's right. And so the same number of carbons, the same number of hydrogens, higher boiling point, lower boiling point. Okay? What will I expect on an exam? I would expect that you would be able to look at a series of molecules and be able to rank them in terms of boiling point or some other physical property based on being able to identify the intermolecular interactions. Okay? So it's kind of important to be able to recognize right away what's involved. Okay? Now, polarizability comes into play as well. And what do we mean by polarizability? We're talking about how easy it is to move the electrons around within a bond, within a molecule. Okay? And so the inorganic example is to look at fluorine versus iodine. Okay? Which one's more electronegative, iodine or fluorine? Fluorine. That's right. Iodine is less electronegative. Okay? But which one's bigger? What's the trend as we go down a family? We get larger, right? And so what we recognize is that these larger atoms are more easily polarized. We can move the electrons around a lot easier on this big atom than we can on this smaller atom, right? So what's the physical property difference between fluorine and iodine? What's the physical state at room temperature of fluorine? It's a gas. It's a very toxic gas, a very hard to work with gas. What about iodine? Is it a liquid? It's a solid. Yeah, bromine's a liquid, right? So we go from gases to liquids to solids, okay? Same kind of argument if we'd had bromine up here, right? But iodine is, in fact, a solid. And it's a solid because it has more van der Waals interactions. It's heavier, it has more surface area, and it can form a much stronger force of attraction. Okay? Dipole-dipole interactions are very, very prominent with ketones, for example. That is an example of a ketone known as acetone. What do you all know the use of acetone for? Fingernail polish remover, paint remover. You can go to Walmart and buy this. You can go to Home Depot. You can go back there and you can get acetone in the paint section to wash out your paint brushes and thin your paints and all those kinds of things. Okay? This molecule has the ability to have dipole-dipole interactions with itself. Why? And it has that's true, and so the dipole is permanent or temporary? It is permanent. So are van der Waals forces involved at all here?
Yes.
Yes, but are they the dominant one? No. And so it's all about the dipole, right? And so how do dipoles line up? We know that opposite charges attract. Even partial charges of opposite charge will attract, right? So we will have the negative end of one dipole interacting with the positive end of another dipole. And now these molecules act as if they are heavier than what they really are, right? If you looked at the molecular formula for acetone, just based on its molecular weight, you might predict that it's a gas at room temperature. But it actually behaves as if it's heavier than that, simply because it has these dipole-dipole interactions, okay? So this is pure acetone interacting with itself. Is there any possibility for hydrogen bonding between two acetone molecules?
No.
And why?
All the hydrogens are on carbon.
All the hydrogens are on carbon, that's right. Now if I take acetone and I place it in water, will it dissolve? Think about it. When you remove your fingernail polish, do you worry about rinsing it off in the sink? And it rinses off quite nicely, right? Why? Because it's soluble in water. Why is it soluble in water? That's right, it is polar. The oxygen atom can accept a hydrogen bond from water, okay? And so it can form a soluble mixture, okay? Now hydrogen bonding, again, is really nothing more than a strong dipole-dipole interaction, but it is stronger than a typical dipole-dipole. Notice I'm not giving you any values, right? In general chemistry, you all had values for all these things. Hogwash. I mean, it's great to know, but I want you to know the relative trends, right? Hydrogen bonding is stronger than a typical dipole-dipole. And so we know we have to have a hydrogen atom bonded to either oxygen, nitrogen, or fluorine. And then it is attracted to, that hydrogen is then attracted to the lone pair of electrons on an oxygen, nitrogen, or fluorine. Okay? What do nitrogen, oxygen, and fluorine share in common? Two things that I want you to know. What do they share in common? They are somewhat electronegative. What else? So I guess there's three things.
The gases.
Okay, but that's not particularly relevant here. Not when bounded within an organic molecule. Just the atom itself. What else?
It takes electrons from hydrogen.
Okay, that gets back to the electronegative part. Small, okay. By small, what else can we say? Where do they sit on the periodic table? They're all in group 2, aren't they? Right? And it turns out that things like sulfur, even though they're in the same family as oxygen, sulfur doesn't like to form hydrogen bonds. Phosphorus doesn't like to form hydrogen bonds, even though it's in the same family as nitrogen. And chlorine doesn't like to form hydrogen bonds. Okay? And they all have what? We're almost there. What else do they have around them? Lone pairs. They all have lone pairs, right? Those things are necessary for hydrogen bonding. This is a simple example of water being, two molecules of water being hydrogen bonded. Okay? If you look at the molecular weight of water, what is it? Tiny? Okay, can you give me an actual value for this one? Molecular weight is what? 18, right? What's the molecular weight of methane, CH4? Very similar, right? What's the difference in physical properties? Methane's a gas at room temperature. Water is a liquid. and it's a high boiling liquid. It's got a boiling point of 100 degrees. Hydrogen bonding is responsible for life. Because if you look at just the molecular weight of water at the temperature that the Earth is, water should be a gas. But it's not. It's liquid, and we need liquid water for life to exist, right? And it all comes down to this fact that we can form hydrogen bonds that actually alter the physical properties in a way that we can actually have the chemistry of life occurring on a planet this far away from a star at a certain particular average temperature. Okay? Too cold and it's ice. As far as we know, life doesn't exist. Right? Too hot, gaseous water, problems too. As far as we know. All right, so you all know about boiling point, right? What did you learn about boiling point in general chemistry?
You can use it to identify a known compound.
Sure, it's a physical property that is somewhat unique to a particular compound. Many things can share the same boiling point, but it does narrow down the range, right? If I told you you had an unknown liquid with a boiling point of 100, would you struggle to figure out maybe what it might be? No, you'd probably guess it's probably water, right? Okay. Now, are there other things that have a boiling point of 100? Sure, but it limits the range, right? So when we have the molecule boiling, right, such that the molecules are converted into a gas, we have the boiling point. That is when the vapor pressure of the liquid is what? To what?
The atmosphere.
The atmospheric pressure. So boiling point is not necessarily a constant, is it? We can boil things at much lower temperature by reducing the pressure, right? And we can boil things at a much higher temperature by increasing the pressure. What do you all use that makes use of that little property? Increasing the pressure to increase the boiling point of something. You all drove here in a car probably today, right? Or maybe some of you, right? What in your car makes use of this property? Your radiator. Your radiator's under pressure. Why do they put your radiator under pressure? So that the water doesn't just boil away. It increases the boiling point, right? If you had that open, the radiator cap just open, guess what would happen? All of your water would eventually evaporate out of the system because your engine runs at much larger or much higher temperature than the boiling point of water. Okay? And so your boiling points will trend in this direction. If a compound only has van der Waals forces, it will typically have a low boiling point. If your molecule has hydrogen bonding, it will typically have a relatively high boiling point. And compounds with dipole-dipole interactions will be somewhere in the middle. Okay? So let's look at some examples of molecules that are fairly similar in molecular weight and size. Look at the difference in boiling points. Is that negligible or is that very significant? That's very significant. Pentane, oh, I told you 35, it's 36, my bad. Boiling point of 36 degrees Celsius. It's a liquid at room temperature, but a low boiling liquid. Butanal, so we go from van der Waals only to what? Now we have dipole-dipole. What happened to my boiling point? By about how much? About double. Okay, we can use government math here, right? And going from butanal to butanol, what did I go to in terms of intermolecular forces? Now I have hydrogen bonding, right? And what happened to my boiling point? It went up pretty substantially again, right? Not quite double, but more than just a bit, right? And does that follow exactly the intermolecular force trend? You bet. Okay. You all in lab this semester will be doing boiling points using an apparatus. It won't look exactly like this because you all do microscale. But this is a boiling point apparatus. It allows us to separate molecules based on their boiling point. Where might this be useful? Organic chemists use it all the time to separate one component that's lower boiling than others. We use it to purify liquid compounds. You use it when you're making moonshine. That's exactly right. So how many of you watch moonshiners on Discovery Channel? You seen it? Yeah. They do distillations all the time. Why do they do a distillation? What does it do? It allows us to separate the alcohol, the white lightning as they call it, from what else? From methanol, which is stuff that'll make you go blind, right? To what else? All that other crap they put in there. The water, the barley, the corn, the sugar, the yeast. You would not want to make a batch of moonshine and just drink it straight out of the... I mean, that stuff looks nasty. I mean, sitting there rotting and doing its business, right? You want the alcohol to come out. And you can use ethanol for this, or distillation to separate the ethanol from the other constituent components. Okay. There are also some physical properties other than just boiling point that come into play by looking at the different functional groups. So let's look at solubility. Butane. What intermolecular force are we dealing with? Van der Waals, and Van der Waals only, right? Notice that it is completely, butane is going to be completely soluble in something like carbon tetrachloride. Why is that? What did you all learn in general chemistry about solubility? Like dissolves like, right? So here we have Van der Waals forces. What kind of forces do we have in carbon tetrachloride? Van der Waals forces. And so like dissolves like. However, butane is not soluble at all in water. Why are they unsimilar? Why is this dislike? One's polar and one's not. One can hydrogen bond, the other one cannot, right? There's no way for these things to interact with one another. However, if we look at a molecule like acetone, acetone has what kind of intermolecular force?
Van der Waal and
Okay, it has Van der Waals and dipole-dipole, right? And notice it's soluble in both carbon tetrachloride and water. Why?
the oxygen can accept a hydrogen bond,
Absolutely, and that accounts for the water solubility.
and the methyl groups can react with the nonpolars,
Do we want to say the word react?
not react, interact.
Interact, better word. Yep, so this can still interact with the carbon tetrachloride through Van der Waals type interactions and still be soluble in the carbon tetrachloride. Okay. And so there's an example of the hydrogen bond that we might witness between acetone and water. Now if we look, this will be the last thing that we talk about today. If we look at ethanol versus cholesterol, okay, they are both alcohols. Okay? But ethanol is soluble in water, whereas cholesterol is not. This is why your arteries get clogged up with cholesterol, because your blood is mostly water, right? Why? Why the difference? They both have the same functional group.
The rule that it has to have the one polar functional group for every 5 carbons.
Ah, the 5-carbon rule that I like. That's right. So every group that can form a hydrogen bond, either accept or donate, if you have 5 or fewer carbons for each one of those groups, chances are it's soluble in water. Ethanol fits that bill. Cholesterol doesn't even come close. This is more fatty. Okay, and so it would be more organic soluble or more water soluble? More organic soluble, that's right. All right, I'm going to go ahead and stop there. I will upload the YouTube video on this today at some point, so you can look on the YouTube channel for that. And we will continue with this on Wednesday.